Good evening. I start now. I don't have the grader has not been able to finish, so we have to be patient. We better continue with our syllabus, and we are still on chapter 26. We've already learned about the fun you have with mirrors, with of course flat mirror, which can give you in a gym the impression that your bicycle cycling area is much larger with a lot more people because you have the mirror that gives you the image of everything. So we learn about the tricks about plane mirror, but also the fun you have with concave mirror and with convex mirror. And then we have the simple equation 1 over d object plus 1 over d image equal to 1 over f, the focal length, which is to the people on optical people, it's almost like f equal to ma. It's a fundamental formula, but today the optical industry, their formulas are even much more complicated. That's because their lenses are neither. Yeah, somebody has a question. Yeah, somebody had a question. The lenses are not the mirrors or the lenses are not either straight, plane, concave, or convex, concave, and so on. Like, for example, this lens. Is it one side totally like a plane mirror and one side like a concave? It's not. It is shaped in a very strange way, right? Well, the opticians, those engineers with optics, they have to study and really do a lot more complicated analysis. The simple formula that we had earlier is too simple for them. But we are not going to be involved with that. I would not even try to learn what they are doing. But the eye is the most complicated. This lens, your eye muscles can squeeze it because I'm trying to focus. So my eye will automatically squeeze it. Or if there's a very bright light, then the, what do you call it? The iris will close in order that there not be too much light coming into your optical nerves. And so this is a very complex thing. And when you have, let's say, not a perfect eye, I don't have a perfect eye. I don't know whether you have perfect eye. You may be nearsighted, you may be far-sighted, and there are people that have glaucoma that actually has a much more serious issue, or what do they call it, epiretinal something. Anyway, the optical people, they have a lot of terms for the different medical conditions that you may have with the eye. And one of my friends, he has glaucoma, and it has gotten so bad that now he needs a cornea transplant. Now, I wouldn't even know how anybody can do it, but it is, yeah. And for him now, he says he has to consult a cornea specialist, he has to consult a retinal specialist, he has to consult some other specialist for a cornea transplant. But it's, but anyway, I just wanted to kind of end this chapter 26 with some sense of how it is that people try to make up for the imperfections of our eye, of our vision. Well, first we deal with, this is well, okay, now this is the eye, and you see a distant object. What you need is to now have a lens, and this lens will now take these rays, the ray that is parallel to the axis and the ray that is going straight through the center of the lens, that now this lens, which is your human eye, the lens in your human eye, will focus it on this part. Somebody says you should check. Yeah, you should check on your glaucoma condition early, because apparently glaucoma cannot be cured. They can try to relieve the pressure. Glaucoma has to do with the fact that somehow I don't know, there's a certain drainage issue and so on. But anyway, just be aware, because if you have glaucoma, be aware. And glaucoma can be hereditary. So if somebody in your family has glaucoma, all the more be careful. And if you have diabetes, I think it leads to glaucoma. So be very careful. You know, our human body is not something that you can say, oh, I'm young, I'm strong, I don't have to worry. Be careful. So anyway, let's come back to this. Here you are trying to see something far. Now, without glasses, I cannot see well. But anyway, let's say your eyes are okay. You're still a very young, person. So you can focus this on your retina, and the image would now be inverted, but that's okay. Your brain is used to saying that, oh, if this is an upright tree, the image on my retina would be that this neuron down here will now tell my brain, oh, this actually is up, that one is the bottom. And so I have seen the image of this tree far away. All right, so this is one where my eye is okay. I don't have to focus on anything. It's natural. I already see it. But now if it is closer, then you need to now bring this image to here again. But now this has to be closer, so this image now is larger, right? And what happens is your eye will now have that strength, I guess the muscles or whatever the medical people call it, so that now your new shape of the lens will be such that it will focus this onto here. That is now your eye. Your eye naturally will now want to focus on this. If I'm looking far, I am more relaxed. But of course, for me, I'm nearsighted. If I don't have glasses, it's all blur. But we will see down in the next slide, we will see how it is blur and how people take care of it or help you take care of it. Okay, nearsightedness. Nearsightedness is if without glasses and I now look for a distant object, my lens somehow has already been shaped in a form that is the wrong focal length. It somehow was, I don't know if I was born that way, or some people say it's because you study too hard and, whatever. I'm not sure that it is just because you study too hard that you will be nearsighted. In any case, this lens, the human lens, now focuses it away from the retina. Therefore, by the time you see it, as far as the retina is concerned, it's blurred. It's no longer a sharp image, it's blurred. Well, what then do the opticians suggest? What they then say is you should wear a diverging lens, right? Because what happens? What happens is you now say, oh, the ray is coming from this distant object. You will now want to let it diverge. diverge so that it seems to come from a virtual point down here. And now when it diverges, now the human lens will now focus it over here. So that's how you now compensate. You make it diverge so that now this lousy human eye lens that was not able to focus it well, now you come in and it is more diverged. So now it will take longer for it to focus. All right, think of it that way. You diverge it so that the rays now are not what it was before. It is now a little bit more, diverging. And so now it will take a longer distance for your poor, defective human eye to focus it onto the retina. Well, but that's what the retina says. I want to see it clearly. And so you should wear a diverging lens. All right. And so you see, I now have a lens, and for nearsightedness, I have a prescription for this diverging lens that enables me to see far away. But for close things, I don't need. For close things, I just bring it. And in fact, as I get older and older, I need to bring it closer and closer because my eye is not as strong as before. My muscles are not good at expanding, contracting. And so now, if you have, what is this now? This is just to show you what happened here. The lens creates an image of the distant object at the far point of the nearsighted eye. So what the optometrist does is to prescribe you with a diverging lens such that the image, the virtual image of this distant object is here, so that your poor human eye doesn't have to focus that well. It's just in its natural state and it already can see this well. So that's how you are able to bring a very distant object like as if it is now close by because of this diverging lens. And as far as this defective human eye lens is concerned, it's reading from a comfortable near distance. So that is therefore the treatment that you get for nearsightedness. And then with age, you may have a certain power for the nearsighted eyeglass. But as you age, you have to now visit the optician, every year. The insurance says you can see it every year. And then you can change because your eyesight only gets worse and worse. All right, so that is nearsightedness. I wonder how many among you are nearsighted? Are you all perfect eyes so you don't need glasses? Nearsighted, nearsighted. Yeah, well, I think a lot of us are nearsighted. I don't know, are there young people who are far-sighted? Oh, really? There are. Wow, I don't know. Which is better, to be nearsighted or far-sighted? In our daily life. It's better to be nearsighted? I don't know. I mean, it's an interesting, chat that you want to talk to people about. But eyeglasses for nearsighted, well, this is one where they actually use a formula to figure it out. But I don't think we need to do that. It's so that you want to bring a distant object to this natural focal point, and then the question is what should be the 1/f. So let's not go into it. At least I'm not that interested. All I'm interested in is that I do need a diverging lens to bring the image of this distant object to a comfortable distance that my natural eye can see, and then my natural eye will then see that as, in fact, oh, that tree over there. All right, so that is this simple basic formula that they are using here. Well, they are saying, for example, you have taken a distant object. Distant object, well, you can say it's infinity, it's very distant, and you bring it to a natural point where my human eye will then see. If you are at that natural point, I say, yes, I see. And so that is a virtual image because this is a diverging lens. Therefore, the image distance is now negative and it's 519 centimeters. And then the question is, what must be the focal length? And then the answer is the focal length must be there must be 519. That's the focal length of this diverging lens. All right? Because that's what the optometrist will prescribe. And then you can get a comfortable eyeglass frame, and be able to therefore see far objects as if they are near, which your natural eye can see very well. Is this concept clear? And is this simple application of this basic formula for lenses, is that clear? All right. Yeah. Okay. So now let us go on. Far-sightedness. Well, this is now one where your lens, your human eye cannot see anything near. Your human eye can see things that are very far away. Ooh, it is easy because the lens is already able to bring a far object to be exactly on the retina. But you now bring an object that is close, this lens is not able to focus it here. Instead, it is far behind my retina. But my retina says, I don't see a clear object. I see a blur object down here. So you now say that I cannot see far. I mean, I cannot see near. I can see far, but I cannot see near. Right? Because you're so near, my lens is not powerful enough. It's supposed to be a converging lens here. My lens is not powerful. My human lens is not powerful enough to focus it on this retina. In fact, it is behind. And so what I need now is what? A converging lens to already converge it so that my poor human eye doesn't have to converge it some more. You got the sense now? My human eye is not able to converge. It's not to focus because it's able to focus it only way behind my retina. So if you now bring an object that is close to me, I am not able to increase my curvature here, the lens here. I'm not able to make it now more curved so that it will now focus it on the retina. And what I now need is a converging lens to make it already converge so that it would. So now what do? They say, all right, what I have is a convergent lens such that when I now have this guy that is near, and it now focuses it so that it is as if it came from a farther away object, and it will now focus it here. So that's what this now says. So this shows the rays to help us appreciate the difference. If you have a object that is close and your eye is far-sighted, so it is not able to focus, right? Then what happens is you bring this with a converging lens. It then makes the rays look like it is coming from over here. It makes it look like it's coming over here, and then it is this which sends. In other words, if I were to draw a parallel X ray, as a result of, if you extend it backward, it looks like it came from here. It makes this, how do we want to say it? I'm already helping. Oh, another way of saying it, which is actually easier way to understand. This is not powerful in converging. I need another extra lens to converge so that it will now focus it here rather than behind my retina. And that is the role of this converging lens. Is that an easier way to understand? I am not, my natural lens is not able to focus on this near object. So what I need is to now to have another converging lens to add to the power of my natural eye, such that together it is now more converging to bring it to my retina. And that's why I need a converging lens. And then if you draw the light rays, it seems to have come from a comfortable place, because it will seem to have come from what my natural eye without without an added lens can see, because I'm farsighted. I see very well without an eyeglass. Anything that is here, I say, yes, I see very well. That is a, CVS pharmacy in front of me, or there's a Walgreens in front of me. Well, what I now need is to have, and if my object is close, then what my comfortable far-sighted distance should be, I need an added converging lens to help me make my total lens with my converging lens and my own poor human lens, that together it is sufficient to focus it here rather than behind. Is that concept clear? That picture clear? I mean, we don't have to be the optician. Optician, you then have to do a lot more, study of the prescription. All right, is that clear? All right. Okay, so now the opticians, they will tell you the power of the lens that you need, whether it is the diverging lens for nearsighted people like me, or the far-sighted, the lens, converging lens for the far-sighted people. They do it in terms of diopters. They don't say, oh, the focal length is so many centimeters. So what do? They will call it the refractive power, and it is 1 over the focal length that you need in meters. So if the focal length is 1 meter of a lens, like for example, for the nearsighted people, you have a diverging lens, and the diverging lens is, what was it? It was minus 640 centimeters. Well, then number of diopters is more than 1 diopter, because you do it in meters, right? So it is, you measure this then in what they call diopters. Now, when I was young, my eyeglasses was 1 diopter focal length. But as I'm getting older and older, I don't know now what's my diopter, because my optometrist doesn't tell me in diopters. They just say you have 20/20 vision, and we now prescribe this so that you have, what is it? They call it 20/20, and then what do they call it? 40/20, and so on. They use a slightly different language. Does anybody know what is a 40 and 20, 20/20, 40/20? Well, we are not the school of optics, optometrists, so we just leave it. They have a certain unit, and the technical unit is diopters, but now the people who are the optometrists, they don't say it in diopters. They say it in this other language. And the rest of the chapter, yeah, it's about the distance. What is your 10, 20, and so on. A person with 20/40 vision sees things at, well, can somebody read it? See something at what? Somebody had a chat that had a remark. Can somebody read it?
A person with 20/40 vision sees things at 20 feet that most people who don't need vision correction can see at 40 feet. This means that they are nearsighted, but only slightly. A person with 20/40 vision may or may not need eyeglasses or contacts. You can discuss this with their doctor.
Yeah. You see now the thing. When they say 20/40, they refer to feet, right? What you should say, what you see comfortably at 40 feet, they bring it to 20 feet, right? That is not international unit. This is international unit. But the people in this country, when you go to see an optometrist, they do it in terms of this language, 20/40 or 40/20, to refer to so many feet that you are comfortable to see if you're far-sighted, you can see anything beyond at 40 feet. But what was it now? No, if I'm nearsighted, I cannot see anything beyond 40 feet. Is that what it is? No, I cannot see anything beyond 20 feet, and I need to bring it. I don't know. I get confused with the language they have. But just beware, if you go overseas, the people who are prescribing for you, they don't go by 20/20, 20/40. They go by diopters. Right? Just be aware. We're not going to be responsible for that on any test. You are not going to be tricked into those, but this is just sort of to get you a sense of this thing about the human eye, because after all, we all live with a human eye. Yeah, it's good to know, but not. But if you are going to be going to the school of optometry, oh, then you need to learn the language of 20/40 and so on in this country. But beware, if you were assigned to work overseas, it is diopters. Well, there are also other things about the magnifying glass. Well, we will not do it. Uh, we will not do it. All right. It is, well, I think we already kind of mentioned that when we talked about uh, solar eclipse, didn't we? Namely, the angular size of a moon depends on how far away it is from the Earth. And when it passes before the sun, if it's just the right distance, it will cover the same angular displacement of the sun. And that's how you will then get the solar eclipse where you see the solar flares. But if the moon is in fact further away, then it will not be able to cover the entire sun. And then what you have is the annular eclipse. So this one is just saying that compare the angular size of a penny held a certain arm's length with that of the moon, and you can work out the numbers. This is just from the circular, the angular from 203. All right. And all these things about compound, microscope, the industry spends much money in designing, and they have to do a lot more of the analysis of what kind of lens here, what kind of lens here. And the thing that we will begin to see in chapter 27 is that when they develop these instrumentations, they don't want your microscope to have all those rainbow colors, what they call chromatic aberration. You want to see what it really is. You don't want there to be fringes. You don't want there to be distortions, spherical aberrations, chromatic aberrations. So they spend a lot of money in designing exactly the kind of lens, the shape of the lens, the distance. Oh man, it's it's not something that we as laymen would be interested in, unless of course you become one of their workers in their factory, in their lab, or then you will be doing a lot of such tests and trials with different shape and with different material. So yeah, this is what they call aberrations. And when we come to chapter 27, we will begin to learn some of the basic things that can happen to your image as a result of the fact that light is not just a single color. Light is a mixture of colors. Light has violet, indigo, blue, green, yellow, orange, red. And when you have the light coming in from the sun, oh, you're going to have the red and the violet come at different places. So if I have a microscope and I want to look at the sample of whatever I'm looking at, I don't want there to be those kind of coloring around, because then I would not be able to tell whether this is actually whatever sample is a good sample or a bad sample. Okay? Any questions before we close chapter 26? And as I mentioned earlier, the basic single concept is this reflection, and basic concept of, oh, we also had in 26 the spherical and the convex, and this question of Snell's law, and the fact that the Snell's law, the index of refraction, can depend on the wavelength of the light. If it is white light, it is a mixture of all of the different colors. But all of the different colors have different index of refraction. And so there can be a set of rainbow colors that come out of your prism, a set of rainbow colors that come out from your lens, because of the lens is made of glass. So there will be a separation of colors, and we need to be aware of that. And you have for the rainbows, this beautiful primary rainbow with the order of the colors, red first, red, orange, yellow, green, indigo, blue, violet. But if you now go into the actual lens law, thin lens, it is that very simple formula, 1 over d object plus 1 over d image is equal to 1 over f focal length. All right, if there are no questions, let us now go on to chapter 27. Is that okay? Okay, so now let me now stop this, and I will now go to now I have to what? Interference, right? Do you see it now? Now, here there is some very interesting concepts of physics, principles behind it. And so we will spend a little more time than just the fun we have in chapter 26. Well, first thing we need to remind ourselves is that if you have a wave and you have two waves that come and they pass through a certain point, they meet. I have a ray that is polarized, and it is polarized so that it now is all coming in, in the y direction or in the z direction, whatever you want to call it. And if I have two rays that are now meeting at one point, they can either constructively interfere or destructively interfere. Why? Because if this wave is oscillating at a frequency, so it has the whatever wavelength, and it is, let's say, red light, so I know what is the frequency of red light because I know the wavelength of red light. And if this one is also red light and it is now coming in, and it was already in sync in the sense that in phase, namely when this one is up, this one is also up. When this one is down, this one is also down. Now when they meet, this one is up, this one is also up. What happens? They add up, right? This one is up, this one is up, they add up. So therefore this becomes a bigger. So this is what they call a constructive interference. And now it does not matter that my train of wave, the wave train, that in fact it is so many seconds later, so long as the difference between my difference in time, that we only differ by integral multiple of the wavelength. You know what I'm trying to say? You are a wave and you have a certain, let's say at time t equal to 0, you released a wave and it was coming. Namely at time t equal to 0, you started singing and you, well, okay, let's say sing, because yeah, you started singing, or you started transmitting with your phone, and you started transmitting with your phone. So you sent a certain radio wave of a certain wavelength, let's just call it lambda, and it started. So it started and it came to this blackboard, this your screen here. Meanwhile, I have another oh, my I yeah. Meanwhile, I have another let's say, phone, and it is in sync with you in the sense that it is also, when you are up, I am up, but I did not send my wave. Maybe, it's a few milliseconds or nanoseconds later. You understand what I'm saying? So you are up, I'm also up, but you are ahead of me. Are you getting that concept clear? You are, bobbing up and down, up and down, up and down, and you are all there, but you are ahead of me. But I am in sync with you, in phase with you, Phase. I'm in phase with you, such that when you're up, I'm also up. When you're down, you're also down. It's just that you are ahead of me. But now, if you're ahead of me by 2 wavelengths, 3 wavelengths, 6 wavelengths, doesn't matter. We would still be in constructive interference. Now, is that concept clear? Because it will be very important for the latter part of this chapter. It's this interference issue. Are you okay with that concept? Do you grasp that concept? Yeah. I am in sync with you because my phone and your phone, we are actually both, part of whatever circuit there is. And it's just that you started to transmit 3 seconds earlier. Now, me, I was still happily, in here until somebody pressed the button to send, right? So we were both dancing, in terms of whatever electromagnetic oscillation. We were both dancing, and then somebody on your phone pressed that button and it sent the wave out. So the wave was traveling. It traveled 3 seconds earlier than mine. Mine, I didn't start it, send till, let's say, 3 seconds later. But now we are in phase. So even though you're out there in space and you are, let's say, up, I'm also up. I'm far behind you as the train. Well, when you now are over here, and now when I now, have a wave that is catching up with you, it doesn't matter that in the end, when I catch up, it was 3 wavelengths away, 4 wavelengths away. When we meet, it would be constructive interference. Because a signal, like a light signal, a wave signal, is actually infinitely long train. It's not like a train from Penn Station, which is very short train. This is a train which is infinite. But now I now send a wave, and now this wave took a little longer to reach you. Why? Because I sent it to reflect off this surface. I sent it off to reflect that surface. I made my wave go more places, but we were all in phase. But you just came straight from Bronx, and you came straight down towards City College. And me, I was we started the same time, but my wave reflected off the big apartment building right over GW Bridge. Is a big, tall, 50-story building. And so it went this way and that before it came to City College, before it was reflected and came to City College. And its wavelength is the same wavelength because we were in sync. We were already sort of chatting on some circuit or other. And then when my wave comes and it meets you, if we are still in phase and we only differ by, let's say, 3 wavelengths, 10 wavelengths, whatever, it will be constructive interference. Am I making myself clear? We had to sort out this concept of interference. That's the key concept of interference. Are you okay with that? Okay. Now, okay. Now, this is constructive. They are start out in phase and arrive at point in phase, leading to constructive interference. And whatever's the length, this one is L1, this one is L2. If L1 and L2 only differ by m lambda, it will be constructive. And as I said, the reason why my source 2 travel longer distance than you was because I let my source 2 hit against the building that is the tower building. I don't even know the name of that building that is near GW Bridge. And so my light of the same wavelength as your light, my light reflected off the tower of GW Bridge, and then it now came to City College. Your wave of the same wavelength was directed straight at City College. So my wave had to travel longer distance. L2 minus L1 is m lambda, then that is constructive interference. Okay, let's grasp that very clearly. Okay, now, what if we are exactly 180 degrees out of phase? What does that mean? That means that when you are up, I'm down. When you're down, I'm up. We are 180 degrees out of phase. You know, to be a full cycle, it has to be 360 degrees. So for you to be up and up, it has to be 360 degrees in the language of the phase angle. But when you're up and I'm down, we are 180 degrees. We are out of phase. Well, if we are exactly 180 degrees out of phase, what happens when we meet? What happens when we meet is we kill each other, right? Because you're up, I'm down, you're up by 3 nano, whatever, meters, distance, meters, let's say. This now it's 3 nanometers, I'm down 3 nanometers, you add them together, that's 0. Therefore, if our two waves arrive and the distance is m plus a half, namely whatever it is, I am now 2.5 the wavelength. Then you are up, I'm down, and we kill each other. We get destructive interference. So this is the condition for destructive interference. You have a wave, a light wave, whatever, radio wave, at the given wavelength. If we were actually coherent, and this is another language used by scientists, if we were coherent, means that we are in sync, we are coherent. Then my second wave, because I sent it on a mission and it bounced off, I don't know, Statue of Liberty. It bounced off this, it bounced off that before it arrived to meet at the City College. Then all I have to ask is, what is the difference in terms of the number of wavelength? And if it indeed differs by half integral, like it is 2.5 or 7.5 or 25,000 and a half wavelength, then there will be destructive interference. Yeah, it is still in sync. It is because it is in sync that it now becomes silence. Incoherent is one where I have an oven here, or oven will be, and you have an oven over there. Oh, they are never going to be so, they are incoherent. So the waves that come from your oven, the waves that come from my oven, they're not going to kill each other. Only if they really were coherent. They came from, you know about laser, right? Well, that is too advanced for you, but it is a technology where, in fact, you have coherent light that comes after it has bounced off a laser. Laser is where the light beam has been bouncing off inside, and then it now comes out of this thing, and now that is a coherent. It is a very powerful beam, and people, you can be blinded if somebody points a laser, powerful laser gun at your eye. But do you at least now get a sense of, for coherent, if somehow the scientists or the engineers are able to make it coherent, that there will be interference because of the fact that your rays, your ray 1 and ray 2, will now interfere. They all have the same wavelength. They interfere depends on how far your ray wave number 1 and wave number 2 has traveled. Okay? I'm drumming this into you because otherwise you'll be confused very easily later on. Okay? I mean, the formula is easy, but just to understand it, that's the hard part. And this m is just an integer, because I sent this wave bouncing around. You remember this fiber optics? Inside a fiber optic, your light, in fact, gets totally internally reflected, and so it will go zigzag around, right? But if I have another, if I have the same source, but now I go by a different path, I can then have constructive or destructive interference at the end of my fiber optics, depending on the path. One went through 1,500 bounces. The other one only went through, let's say, 5 bounces. Well, will they interfere constructively or destructively? Well, depends on your calculation. You say, well, I actually went and calculated L2. The poor guy had to undergo 1,500, reflections, so it had a longer path at the same wavelength, at the same frequency, versus this other one. Okay? Are we able to now understand this concept? Okay. All right. So now, what is this? It's the same thing. Oh yeah, this is just to say that for this to occur, the source has to be a coherent source. That's the technical name for it. It has to be a coherent source. Because if it's not coherent, then my oven now has atoms that are bouncing around, and this my oven has also atoms bouncing around, and they're not coordinated. They are not saying, hey fellows, let us start dancing only at the beginning of the conductor. Because if you have a conductor that says, now begin, ka-dum, ka-cha, ka-dum, ka-cha, then you are coherent. You are jumping up and down and up and down. But if it is a, a noisy gathering, you have a concert going and then everybody is yelling over here and I'm yelling over there, there's no constructive or destructive interference. You just get a noise. N-O-I-S-E. All right? Now that we have sort of grasp this thing about interference, whether it is constructive or destructive, we now want to come to this thing called Young's double slit experiment. Oh, I should have checked on who is this Young, Y-O-U-N-G, because it's for optics, it's a very important name, Young's. What this Young's double slit experiment is, and it's important because in all of these applications for the optical industry, you want to have a slit so that you will now pass the light through, like Polaroid filter and so on. You want to now sort of shine light that came from a source, whatever is the source, and now you want to let it pass through double slit. Now, if you have a double slit, you would have imagined that the image over here should be just simply two bright slits, because the light should have gone through and it would be bright here, and the light gone through should have been bright here. Instead, what Professor Young, Y-O-U-N-G, I guess he's not old, he's young, what he found, and I guess in the lab, in your lab, one of your sessions, you will do that upstairs on MR4 somewhere, 407 North or something. You will do that experiment. You shine light on a double slit. You would have thought the image, the shadow or the image of this would have been two bright, slits. But instead, what do you see? You see fringes. You see bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. That proves that there is interference. That shows that indeed light, they are constructively interfering here so that they make it bright, and then destructively interfere over here, dark and bright and dark and bright and dark. Now, this is true only if this is light of a single wavelength. If it is not a single wavelength, you will then have bright, let's say red, and then dark red, bright red, dark red, but then you will have bright green, dark green, light green. So it will be a lot of rainbow colors mixed up all together. But if it is a pure single wavelength, then you will see a very clean separation. So that's one way in which you can kind of like check your instrument, whether your instrument has a clean, pure single wavelength, or is your instrument with superposition of wavelengths. All right, so this is now the simple aspect of Young's double slit experiment. This is what you will see, and when you go upstairs to do the lab experiment, there will be a formula that you will find useful for analysis. Oh, the question was, will you always only see 6? No. It depends on how far away your image, your screen is from this. Because the further away, then the more of these slits, the fringes you will see. All right, but of course, the brightness of this fringe gets not as bright as you go further away. Why? Because the light has to travel from here to down here. So it will be less. I mean, not as less as my human eye would, but it will be less. And it really depends on how far away is your screen. Okay? Good question, because the formula will tell you how it is. So let us come to, again, this double slit. And they say there's slit 1 and slit 2. And this has to be a small slit. The gap, the slit has to be small. And for the technical experts, there are additional complications if this one is too thick, too wide a slit. In other words, if I have two wide open doors, I'm not going to see the beautiful experiment that I saw here. If these slits themselves were too wide, I won't see this beautiful, clean, fringe, because something else happens. You will learn later, okay, in this chapter. Again, another physics aspect of it. But so let us just simply say, oh, there is somewhere a nice small slit, slit 1, slit 2, and it is separated by a certain distance d. I guess they should give you, they don't, or they will give you this is d, the distance between the two slits. And now you have the light that passed from slit 1. It can, of course, come to this image point. The light from slit 2 can also come to this point. And the light that passes through slit 1 and slit 2 are coherent. Why? Because you have to go back to this picture here. They came from a single source. All right? They came from a single source. So they are coherent. And it was a given wavelength, whatever is the single wavelength. So it's coherent and it's coming from a single source. So I have a coherent source of light at a given wavelength lambda. And it now, yeah, that's the question that we will now come to. You are asking a good question. That shows that you're awake, yeah? Okay. So now let us draw this. So first, over here you can say, well, I can sort of see this should be bright. Why? Because this distance is equal to this distance. So this is constructive interference, right? Because L1 and L2 is the same. Therefore, it is M equal to 0. And this is totally constructive. And now you say, where is the next bright image? Well, it is one where this length is longer than this length by one wavelength. You see the trigonometry? You have to be very good with trigonometry, your algebra has to be good and your trigonometry has to be good. Your calculus can be, non-existent. Although it would be good to have a little bit of calculus. Anyway, so you now say, where would the next bright image be where it is constructive interference? Well, that would be one where this distance from this slit to here versus the distance from the second slit to here is differ by one wavelength lambda. Well, okay, so now you can see. Oh, and then they say, where would there be a dark image? Well, the dark image is where the difference between this path and this path is half a wavelength. Because if this distance is longer than this by half a wavelength, since they were coherent, they were in sync, they were in phase, but when they arrived here, when you are up, sir, I was down. Exactly, when you are up, I was down. Therefore, we kill each other. Therefore, this is dark. So this point is destructive interference. Yeah. This dark image is because there was destructive interference. This bright fringe is because there was constructive interference. You got it? And this wavelength is fixed because we all came from a given wavelength. Whether it is blue light, whether it is neon light, whether it is red light and so on, or yellow light, orange light, I don't know. And upstairs in Marshak room 4, I don't know what is the source they have, but for a given wavelength, then you will now know there will be a bright fringe here, bright fringe here, and the dark fringe will be somewhere here. And now you can do the, well, there's the central or the zeroth fringe. Then you have the first fringe away from the center. And you can see the intensity goes down a little. Because why? You are further away from my actual original source. All right? And so now this is to actually get the formula. Just now there, it was just to get the concept of when would it be bright, when would it be dark. But now we can go and say, let us now apply our trigonometry in order to get the precise location, angle, where you will find a bright fringe, the angle where you will find a dark fringe, okay? So we now draw this, and we now say, well, let me now look. The distance between slit 1 and slit 2, I call it D. That's just algebra. We call it now D. And we now say that the angle where this fringe will occur, the angle relative to my original direction, horizontal direction, let's call that angle theta. And we now want to know, when would this be exactly constructive, let us say. I don't know whether we can see it. The difference in the length between this and that is now this delta L. And if I now use trigonometry, delta L is d sine theta. All right? And now, what I now want to know is, what is the angle where there's a bright fringe? Well, the angle where there's a bright fringe, I can now say bright fringe occurs when sine theta is m lambda. So there is m lambda over d. Because if this is exactly integral multiple of the wavelength, they will be in constructive interference. And so this then would be the formula. Bright fringes of a double slit experiment occurs when sine theta is m lambda over d, where m can be 0, 1, 2, 3. And m equal to 0 is where it was all direct, so that the image of this double slit is a double slit over here. That's at angle theta equal to 0. But m equal to 1, m equal to 2, m equal to 3, they go further and further out. And now dark fringe. Dark fringe would be one where you now say that the difference, the delta L, is now m plus a half. Because in order to be interfering destructively, you have to have exactly an extra half wavelength. So if it was, let's say, 2 plus a half, oh, then when you arrive, you were up, I was down. So the destructive interference, which is when you have the dark fringes, is when your angle sine theta is m plus a half lambda over d. And when you are in the lab, you were told what was the wavelength, and you have measured what is your double slit separation d, and you can then say, oh, it will occur at this angle. I suspect when you do your experiment, it is rather that they don't tell you what is the wavelength, and they say, you figure it out. How the, not how the heck, but how do you figure out the wavelength? What you do is you measure the angle, of your bright fringe, and then you measure this slit D, and you then say, okay, I know that this one is m equal to 2, or you will measure m equal to 1. And I know, therefore, this is 3/2. I know my angle theta, I know my trigonometry, I know my D. Therefore, uh, you lab instructor, the wavelength of the light that you gave me to shine on this double slit is so many nanometers. Okay? Are you okay with this? What does that symbol in image A represent? Where's image A? Oh, this is just to say that you want to now look near the double slit. The actual thing is one where this and that, they are going, right? But you want to now look at this near the slit so that then it is coming out in this direction.
Oh, so that represents the whole image. It's just like a zoomed in.
Yeah, that's right.
Okay.
You zoom in to this part of it. So when you zoom into this part of it, it's like this one is now also going in the same angle. But of course, the actual thing is not exactly this way. The actual thing is what we showed earlier. Let me see. Yeah, what we showed is like this, right? So you can say this one and this one, the angle is not exactly the same. But you are now making this very small and making this very far. So you're zooming in on this. And again, for the real engineers, they will have to do the whole calculation not so easily. They have to do the whole thing by drawing this and drawing that, and then go through all of the actual trigonometry. Here, we are simplifying by saying I zoom very close to the slit and make this D small. Then over here, what comes out in the direction of your slit number 2, M number 2, is they are parallel.
Professor,
Yeah,
I have a question.
sure.
For the second one, for B, how is the light able to bend sideways? How is that possible?
What do you mean by bend sideways?
Like it's not going
Oh,
straight.
that's also a very good, that's how science progresses. Young's double slit experiment was done, and then they just go blah 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 blah, right? And then someone like you says, how is it possible that my light will bend to begin with? My light came this way, why did it bend? Isn't that your question?
Yes.
Huh? No, it's a very interesting one, right? And so later we will learn there is this Dutchman, I think, Huygens, Huygen, Huygens principle that says that, this wave front is radiating all over. And we will come to that. For the moment, we are not yet there So what you're asking is how it actually was. Young's experiment, they were done, and they all say, whoa, I can now sort of understand this, fringe, but there is a lot more physics involved. There is diffraction, there is Huygens principle, and so on, which we are coming to. So chapter 27 is actually very interesting because it is a lot of science principles inside. Okay, good question. For the moment, we just simply say, all right, I don't know, light can bend. And then you can say, oh, I can now at least understand the reason why I have bright fringe, dark fringe, bright fringe, dark fringe is because of interference. Yeah, we will learn it later. It's very interesting. And when you come to it, I will spend a little time saying who is Huygens. It's a very interesting principle, which once you understand it that way, you say, I now understand. Your horizon become bigger as a result. Okay, so now they say, well, I have red light with slits separated by 0.00012 meters. That means that it is what? 0.12 millimeters. I don't know upstairs in your lab what is the D. I don't know if it is 0.12 millimeters, but anyway, they have already checked it out, so it is the kind of slit distance which makes it observable, easily observable. So this is then the D, 1.2 times 10 to the minus 4 meters, and the distance is 2.75 meters. And they want to now know what is the distance on the screen between 0, which is the image of this slit itself, and m equal to 3. Well, that's just a straight application of that formula. We say sine theta is m lambda over d, and lambda is, we are told it is 664 nanometers, which is close to red light. And you therefore say the angle from here is a sine, the inverse sine, a sine or arc sine of m lambda over d, and m, they say they are interested in the third bright fringe away from the central one. So m is 3, lambda is so many nanometers, and d is 1.2 times 10 minus 4, and voila, it is 0.1 degree, 0.9, it's almost 1 degree. So you can then see that indeed you can sort out the fringes, bright fringe, dark fringe, bright fringe, dark fringe. Okay? And you can then see, oh, what is the actual separation? The actual separation by trigonometry is L tangent of this. And so you can work it out. It is L is 2.75 meters, and the angle is about 1 degree, tangent of 1 degree, and by the time you work it out, it's about 5 centimeters. So that's about 2 inches. So actually, in the lab, you can measure that separation, right? It's about 2.5, 1 inch is 2.54 centimeters. So this is about 2 inches. Okay? Any question at this point? Okay, good. All right, now, this is showing a result. The figure shows a photograph that illustrates, the kind of interference fringes that can result when white light is used in Young's experiment. So in other words, you now say, I have this Young's double slit experiment, and I have my double slit that is, whatever's the distance, so many point, so many millimeters separated. But now I don't have a single wavelength light. I have mixture. I have red, blue, green, yellow, and so on. And now they say, what is it that you see? Well, they had some student come by and then they actually did it. And of course, in the middle, it is white. In the middle, it's white because all the lights, their central fringe is bright. So it doesn't matter whether it's red or blue or green and so on, they will, whatever it was, combination, which you call white light, they will now all come here, they become white. Is there any question about that? No question, right? That's obvious. That's trivial. But you now have to say, what about those outside fringes? Well, outside fringes, now the bright fringe for red light is different than the bright fringe for green light. You remember? Here, we have that formula here, right? Here. Red light is longer wavelength than green light. So if you want to look for the bright fringe, m equal to 3 or m equal to 2 or whatever, a given m, let's say m equal to 3, the red light will be a bigger angle than green light. You got the idea? You got the idea? Is that, yeah? Red light, the wavelength is longer than green light. Therefore, the angle for the bright fringe of red is bigger than the angle for the bright fringe for green. Voila. That's what it is. The bright fringe, red, is further away from the center than green. You see? And then there's this red and green, and then red and green. But down here, it's getting more blur because there is more different colors now mixed up here. So this then says that if you look at it carefully, you'll find that the red bright fringe is further away than the green bright fringe. Okay? Are you comfortable with this? Especially if you're going to be doing the experiment upstairs, it would be good to at least grasp this. Okay, all right. So it's all based upon this formula, right? Why is the central fringe white? Well, we already answered it. It's white because everybody, the bright is right in front of you, and whatever is, you have the red and the blue and the green and the yellow and all that, they become white. Well, of course, then this becomes white. So why is the central fringe white? You say, obvious. Even a child can answer that. Now comes a more interesting question, again involving thin film interference. This was double slit, but now we come to thin film interference. And here it is very interesting for some technical reason which we only leave it to the experts, but we got to now just sort of like recognize it or use it or just say, yeah, that's what the experts tell us. I have a ray, a light ray, incident light, that now reflects off gasoline. Gasoline is over water, right? So, I mean, it happens all the time. You have oil, spill oil on the water, and we've all seen this colorful effect of that. You must have seen it. and you can recognize it. If you see a patch of oil, it you know, there's some sort of like gleam to it, you know, colorful aspect to it. That's what we are talking about here. Okay, so you now have light ray coming to this gas or oil, little oil, right? Call it gasoline or oil. And now light will be reflected off that. Okay, light will be reflected off that, but there will also be a transmitted one. Okay, now when it now comes in here, it will be reflected off the water. Why? Because this index of refraction is less than this index of refraction. Okay, are you comfortable with this now? I now have one light ray that came up here, boing, it got reflected. But now I have the other guy that says, ooh, I can plunge into the oil, right? Into the oil, and it will now go on. So this is the refracted ray. Remember that's Snell's law, right? It is the refracted ray. And then it comes here and it says, ooh, uh-oh, this is water. The index of refraction is higher. I will now be reflected off this one as well, right? And so now I, meaning me, I have my wavelength. Whether it's red light or green light, I don't know. Whatever is the light. Somebody had a question? Oh, somebody had a question. What was the question? What's the question?
I said the light bends because the median changes, right?
Yeah, here, right. There is reflection, that's we already know. And then there is this refracted ray, and it is now also reflected here, right? And now the wavelength here in air is different than the wavelength in the oil, because the velocity of, or the index of refraction is bigger here, and therefore the velocity of the light inside this oil is now slower than the velocity of light in air. Is that the, I cannot write on this guy. Yeah, I tried to write on this guy, but now I have all lost this ability to write. Pen. Oh, can I? Does it show?
Yes,
No.
it did, but you erased it.
But I didn't erase it. Why? Why? Let me write down here. See? Well, okay. When I upload it, because I will. Let me just describe it, and then you will kind of see. Wave velocity of light is equal to the wavelength times the frequency. Remember, any wave, you remember that from 203? But also here, you know, the velocity of light is lambda times f, frequency. But now, the wave velocity of light in a oil or in a denser medium is slower, because the velocity of light now, it has to, you know, interact with all these molecules in there, and so it is not as smooth as before. it has to now slow down. I mean, I'm just giving you a very intuitive picture. The actual thing involves more sophisticated analysis. All right. So the velocity of light in the medium is less. So you call it the index of refraction. The velocity of light in the medium is c over n, n being the index of refraction. But the frequency remains the same because my electric field is still oscillating at this frequency, and it is coming in and it is now in the water or in the oil. It is still at that frequency. It's just that now your wavelength is now shorter. You got it? Because the wave velocity, c is lambda f. In the medium, c in the medium is smaller. Oh, no. It will. There will be some light that actually goes down. But we are interested in the interfere. Oh, where's that now? Now this doesn't show? Ah, yeah. Now my mouse doesn't show? Okay. All right. We are interested in, do you like a laser pointer rather than my mouse? Doesn't matter, right? We are interested in what is the it's fine. What's the interference between this wave and that wave? Of course, my friend, you're right in saying that there will be light that actually went further down. But then when they further down, they're not going to interfere with me. We're looking for interference between this wave and this wave. We are not interested in what happens down here. Of course, it will go down some more, and it may not be reflected anymore. It will just simply illuminate whatever is the bottom of the tank. All right? So we are not interested in what happens there. Let the people who are interested in following what's the apparent depth and so on, let them handle it. We are interested in, gee, what is the interference between this wave that got reflected here versus this wave that went further down and then got reflected and came back up. All right. So we are interested in now what they call the thin film interference, because this is thin. The oil is a thin film. So this is called the thin film interference. We want to know what is the interference between them. But now there is a sort of thing that we have to accept. And now we won't be able to say, how did you figure out? Because to figure it out, you have to then basically take an optics course and then go through the boundary conditions and so on. So let's not do it. We are like children. We just want to get the overall concept. All right. So now there is one thing here. Well, now why doesn't it go? Gee, somehow I am now out of, oops, what did I do? What do I do now? What do I do? Let's say I don't want laser pointer. Now I'm back here. Okay. Okay, yeah. All right, I have it after all. You see, index of refraction is, let's say, bigger than 1. So the velocity in the medium is now slower. That's why you have a index of refraction. C is the velocity of light in vacuum, in air. All right. So this is the vacuum times frequency. This is the medium in the film times frequency, and the frequency remains the same. Therefore, in a medium, the wavelength of light is now shorter, smaller. You got it? somebody asked the correct question. I went through all of this really for nothing because my memory is not that good. I had already done that, but I forgot. All right, so this then says that the actual wavelength of the light in this film is actually smaller than the vacuum. So lambda of the film is lambda vacuum over n, where n is the index of refraction. Okay? All right, so now we want to focus on this, but there is now a question of what is the nature of this interference. And as we have said earlier, if this is, and this was actually from, that if they were in fact 180 degrees out of phase, the net would be exactly 0. So that at the surface here, there is no oscillation, no amplitude, and therefore the wave gets 180 degree phase change. It is one way, easy way to figure this out. Say why? One easy way to figure it out is to say, if I'm in air, oh, my electric field, oh, it is able to go up and down, up and down. But when I now come to the water, let's say, or this medium, which is denser, the medium, those poor atoms, they cannot, they are not as free to bounce around. The ones that are inside the medium, yes, they are bouncing around. But at the surface, they are sort of like, they cannot do much. They cannot dance. The guys that are inside, they are free to dance. But those guys on the surface, they can't. And therefore, when you have a light coming this way, the reflected ray and the incident ray, they will cancel each other so that there is no electric field near the boundary. So there is a 180 degree phase change when you go from less dense to a more dense medium. We just have to accept it, but I'm trying to give you a picture that makes it easy to sort of accept it. You need to do the boundary conditions, the optics, to figure it out, to accept it. But a sort of naive way to accept it is to say, my poor atoms down here, the electrons in here, they are not free to oscillate, but the ones that are down inside, deep inside, oh, they can dance. It's just that the wavelength is, shorter, that's all. All right. So in reflecting from the wall, a forward traveling half cycle becomes backward traveling half cycle. There is a 180 degree phase change. All right. So this is then the rule. There's no name to this rule because it's not so deep that you then associate a name like Huygens or Young's or some of the other scientists. When light travels through a medium with a smaller refractive index and get reflected at the boundary to a denser medium, oh, the light will be reflected with 180 degrees out of phase. Okay, it will be 180 degrees out of phase. But when light travels from a larger, more dense to a less dense, there is no phase change. It's sort of like a rule. So from a less dense to a dense one, oh, there is a 180-degree phase change. But when it is, this side is dense, that side is less dense, then that reflection, there is no phase change. All right. So now, using that, we will now try to figure this out. A thin film of gasoline. Oh, this is already 640. Let me just pause it and then we can stop. This is 640. A thin film of gasoline floats on a puddle of water. Sunlight falls perpendicularly on the film and reflects into your eyes. The film has a yellow hue because destructive interference eliminates the color of blue from the reflected light. The refractive index are 1.4, 1.3, determine the minimum non-zero thickness of the film. And before we quit, let me just mention that this is less dense to this. So actually, was there a 180-degree phase change here by the rule? Yeah, right? So there was a 180-degree phase change. But now, when it now came down here, was there a 180-degree phase change here? No. And therefore, when it comes out, is this one 180-degree phase change relative to this? Extra. I mean, of course, there's a phase change here, which is due to the fact that it had to go extra distance. Huh? I mean, that's a tricky question. But I just wanted you to kind of leave that with you. There was a 180-degree phase change according to the rule. Then over here, there is no 180-degree phase change, but there is now an extra path length, right? An extra path length. And now, but when it comes out, there is no phase change. It just came out. It's not reflected. So between wave 2 and wave 1, there is now an extra half wavelength phase change, in addition to whatever is the phase change due to the path length here. So that's the secret, and we will continue on Wednesday to dwell on this. And I just warn you, the book, if you read the book, is very confusing. So we will have to sort it out on Wednesday, okay? All right, so I will quit here, and I
Professor,
don't have the, yes?
I have a quick question.
Yeah,
Just a little clear up. So you said that the speed of light is what slows down. Is this like,
in medium.
yes, in the medium. Is this because I'm getting confused? Because it's traveling a further distance to get reflected back to the eye, or is it also because the wavelength is shortening, or is it because of both?
Yeah, no, it's really because the light has to interact with the molecules of the medium. And so when the light has to interact with the molecules of the medium, it now begins to slow down, because now I could do punyo, punyo, right? So it has to now slow down. So now the velocity is therefore now slower. And what is the velocity of light in a medium? It is the velocity of the vacuum divided by n, where n is the index of refraction. That's why the wavelength is now shorter, because the frequency remains the same.
Oh, okay, okay, I see. Because the
My
collisions.
frequency,
Okay, okay, okay.
my electric field is still ka-chung, ka-chung, ka-chung. It's still enjoying whatever the music it has, right? So the frequency remains the same. And since the velocity of light is now slower, the wavelength of light in the medium is now shorter. Okay?
Got it. Thank you.
Okay. All right. So, okay. So I'll stop the recording.